A series is basically the sum of all terms in a sequence. So here is a sequence, which is a list of numbers. And here is the series, which is the sum of all those numbers. So remember that to determine if the sequence converges, we take the limit as n approaches infinity. And if that limit is finite, then the sequence converges. But to determine if a series converges, we need to check if the sequence of partial sums converges. So here we take the limit of the nth partial sum as n approaches infinity, and if that's a finite value, then the series converges to this value. And we say that it has a sum S. So the sequence of partial sums can be defined as follows. So we have the first partial sum is A1, and the second partial sum is A1 plus A2, and the nth partial sum can be written as follows. And to actually check this limit, we need to find a closed form expression for the partial sum of the series. And we'll do that in an example. Let's find a closed form equation for the nth partial sum of the following series. Well, we can write the nth partial sum of this series as 1 over 3 to the 1 plus 1 over 3 squared, and so on, up to 3 to the n. And if we multiply this by a third, we obtain the following result. And now if we subtract the second equation from the first, we get 2/3 Sn on the left hand side. And on the right hand side, all these terms here in the middle are going to cancel. So what we're left with is 1/3 minus 1 over 3 to the n plus 1. And now if we multiply through by 3 and divide by 2, we obtain Sn is equal to 1/2 by 1 minus 1 on 3 to the n. And now you can test that this works by finding a few partial sums using this closed form equation. Given this nth partial sum for the following infinite series, determine if the series converges, and if so, find the sum of the series. So if the sequence of partial sums, denoted as follows, converges, then the series converges. And what we do is take the limit of the sequence of partial sums by taking the limit of the rule describing this sequence of partial sums. And as n goes to infinity, we can observe that this term disappears, and the limit evaluates to 1/2, which is effectively the sum of this series. So be careful that you don't confuse sequences with series, because if you take the limit of the sequence and not the series, well, this is going to evaluate to 0, which is different to the limit of the series. Let's find the sum of the telescoping series. So I'll leave it to you to apply the method of partial fractions, and you can write the series in the following form. So the nth partial sum can be written as follows. And now we can group every two terms together. And then we can cancel out the like terms, so -1/2 plus 1/2, and so on. So this -1/4 has another quarter here, and this 1 on n corresponds to a -1 on n before it. So what we're left with is a finite partial sum. And taking the limit of the sequence of partial sums for this telescoping series, as n goes to infinity, well, we can see that this second term goes to 0, and therefore the limit evaluates to 1, and consequently the sum of the series is 1.